So now we're going to return to something we talked about earlier in the momentum unit, and that is the idea of center of mass. So just as a quick refresher, center of mass is the average location of the mass in a system, okay, or for an extended object, and by that I mean something that we can't just treat as a single point, which we often do. So maybe we're talking about a board, maybe we're talking about something that's not uniform, like a baseball bat or a golf club or anything like that. Center of mass is the average location of the mass in that object. And the way we find it is with this equation here, which is simply a weighted average for the position of all the mass in our system. So the problem here asks us to calculate the center of mass we had in the previous problem, which was going back to that equilibrium one that we just did. So I'm going to pull that picture in here to help us calculate the center of mass. So we have our system here, and we had just found that this 3 kilogram object needs to be located 1.73 meters to the left of our fulcrum in order for the system to balance. So I'm going to go ahead and calculate the center of mass of this system here. So now that we have our equation for center of mass, we also need to consider what our origin is going to be, what's our 0 point. And so I'm going to say that this point right here, where the fulcrum is my 0 point. And the reason I'm doing that is that all my distances here are measured from that point. And so now I can go ahead and plug in the things I know and calculate the center of mass. So object 1 I'll say is the 5 kilograms, so it has a position of 2 and a mass of 5. Object 2 is the 4 kilogram. Its position is negative 1.2, and the reason for that is it's left here of my pivot, or of my 0 point. And then we have our 3 kilogram object, which has a position of negative 1.73 repeating. We're going to divide all that by our total mass here, which is 12. And we find if we didn't round it all that our x center of mass is going to be 0 meters. Okay? Which means that the x center of mass is right here on top of our fulcrum. Moving on to part B, we want to state how this compares to the location of the fulcrum, and we can see, of course, that it's the exact same position as our fulcrum, and we want to know why this makes sense using the concept of center of mass. And the reason why this makes sense here is the center of mass is the average position of the mass in our system, which means that the average location of the force of gravity acting on our system is right at that point. And so if we think about the forces that are acting on our beam, okay, with this idea of center of mass, we have the force of gravity acting from that point there where the fulcrum is, and then we have a normal force, or a force from the fulcrum, going up. Neither one of those forces, the normal force or the average position of the force of gravity, creates a torque because they both act on the pivot, and therefore the system balances. All right. So what we can conclude from this is that if we have a system like this, okay, it will balance at its center of mass, because if we place the fulcrum, or whatever it's balancing on, at its center of mass, no torque is created by the force of gravity, and therefore it will balance. This last question asks, if the beam instead had a mass, how would that affect the center of mass and the location where the beam balances? And in some cases, the beam having a mass will have an impact. However, in this particular case, the center of the beam is located at the center of mass of the system. So adding in mass for the beam, okay, would not do anything. All we would have in this equation here is when we add in that term for the beam, its x position would simply be 0. So if we add in that term, it's just going to go away, because the center of the beam is located at the center of mass of the system. This won't always be the case, but in this case, the beam having a mass would not affect the center of mass of the system, and therefore would not affect where the beam balances. So as we just saw in the previous slide, center of mass is also important when dealing with torques and equilibrium. We've talked about it before in the context of momentum, but it also matters when we're dealing with torques and equilibrium because it tells us the location where a object will balance. All right, and we talked about this a little bit on the previous slide, but the key idea is the center of mass is the average location where gravity acts, and therefore if the system is balancing about that average location, gravity will create no torque. All right, and therefore the system will balance. I will say this, obviously trying to solve for the center of mass to figure out where a system will balance is easier. However, it is a little bit limited, and you can't always do everything using this idea of center of mass. For example, if you want to know the force of tension in something, you can't use center of mass. If it's something where there's multiple pivot points or multiple supports, we can't use center of mass. So there are some limitations. But if we just want to know where a system balances, center of mass is a great thing to use. We're going to do one more practice problem here. So we have a beam with a mass of M and a length of L connected to a wall via a hinge, and it's held horizontally with a rope. The rope is connected here to this beam at a point that's 3/4 of the length of the beam and makes an angle of theta as shown here. And we want to derive an expression for the tension in the rope. So the very first thing I'm going to do is simply identify the forces I have acting on my beam and where they act. So I have a force of tension from the rope there. I have a force of gravity from this hanging mass here. I also have a force of gravity from the beam, which acts in the middle of the beam there. And then I'm going to have some force from the hinge. It's going to act something like that, but again, we're going to end up making this be our pivot here most likely, and therefore we really don't care about how much force that hinge creates because it's not going to create a torque. So with that as our pivot, and the reason we're doing that is that's an unknown force that we don't care about, so that's a great choice for our pivot. So with that as our pivot, let's think about the torques we have acting on our system. So we have a torque from that force of gravity acting on the beam, we have a torque from this force of gravity from the hanging mass, and we have a torque from tension here. So now that I have that, I can go ahead and start setting up some of the torques equals I alpha, which in this case will just be 0 because we're in equilibrium. So torque-wise, I'm going to have the torque of tension, and that's going to be a positive torque because it's going in the counterclockwise direction there. And then I'm going to have the torque from the beam and the torque from gravity, which are both going to be clockwise torques, and therefore they're both going to be negative. So minus the torque from the beam, minus the torque from gravity acting on that box, and that's going to be equal to 0. For each one, we can substitute in RF sine theta, so R times the force of tension times sine of theta minus R times the force of gravity from the beam times sine of theta minus R times force of gravity from the mass there times sine of theta equals 0. All right, and I'm going to plug in the things I know here. So for the force of tension, my R is just going to be 3 force L times that force of tension times sine of, and that theta there is that angle that's defined. Minus, for the beam, the force of gravity acts in the middle, so it's going to be 1/2 L times the force of gravity on the beam, which is just going to be mg, because it's the mass is defined here as m. And sine is just going to be 90, so I'm just going to get rid of that term there because the angle between the radius here and the force is 90 degrees. For the hanging mass there, all right, the radius is going to be the full length of the beam, L. My force, once again, is going to be mg because the box also has a mass of m. And that sine is also going to be 90. Once again, we see that the angle between the radius and the force is 90 degrees. And so that's equal to 0. I can go ahead and cancel out the L's because they're in every single term. And I can simplify this a little bit, and I get F3 force times Ft sine of theta minus 1/2 mg minus mg equals 0. Moving those over to the other side and combining them, I get 3 force Ft sine of theta is going to be equal to 3/2 mg. You can cancel out the 3 on both sides here, and I can get rid of the 2 and make this a 2 here, and when I ultimately solve for this, I end up getting that Ft is going to be equal to 2 mg all over sine of theta. And there I have my tension in terms of m, L, theta, and fundamental constants.